The fluid containers below are all filled to the same height. How would the pressures at the given points compare? So the reason that atmospheric pressure is 101,325 pascals is because there's a lot of particles in any given column of air. Take, for example, this column here. If you look at a particle that's located at that position, how many particles does it have above it? A whole bunch. And it could get thinner, the density of particles, as we go up. But it turns out there's quite a bit of pressure here on Earth's surface. It's 101,325 pascals. But now we have to imagine, what if we take a column that goes into some water? And what would be different now? Well, you'd still have all these particles above that any given particle on the surface of the water would have to support, like it would have to hold them up. So when we look at the water and its density, it's a lot more dense than air. And this turns out to increase the pressure quite a bit as you go down in depth. Okay, so we want to actually calculate some pressures underwater, and it's going to be significantly higher than 101,325 pascals. Now, how would this situation compare to, let's say, if we had a smaller tank? Would the pressure of tank 1 be different than the pressure of tank 2? Or would they actually be the same? Well, analyzing a vertical column is what we have to do in this situation. And I hope it's clear that the vertical columns would actually be identical here. And so between them two, they have the same pressure. And by that same logic, what would be the answer for P3 and P4? Turns out that what's next to the particles doesn't really matter. It's all about the depth of the column. So same pressure for all of them, actually. But now, how do we actually calculate what that pressure is? We'll use this formula. The pressure is the density times G times the height of the water column. It's important to note, though, that this is not an absolute pressure. It's actually going to be a difference in pressure between the surface of the water and the point at which we're trying to evaluate the pressure. So let's try it here with this problem. Find the pressure on a scuba diver when she is 12 meters below the surface of the ocean. Assume standard atmospheric conditions and a density of salt water approximately equal to 1.03 times 10 to the third kilograms per meter cubed. Alright, first I'll draw the situation. We've got normal atmospheric conditions, so air particles here. The pressure on the surface is going to be 101,325 pascals. Down below the surface, we have a scuba diver. She's got a lot of water above her, so that's going to increase her pressure. So let's find out what the pressure differential would be. We need to know the height below the surface, which will be h. That's 12 meters. We'll use G equals 9.81 newtons per kilogram. And we have a density of water being 1,030 kilograms per meter cubed. All we have to do is multiply these things. And I'm going to call it, in this case, a delta P, a change in pressure. And this is the formula. Alright, our change in pressure is 121,252 pascals. Maybe more than you'd think. That's actually more than atmospheric pressure itself. Now keep in mind, this is not going to be the absolute pressure where she's located. It's just a difference between the surface and her. So if we want to get that absolute pressure, then we want to take the atmospheric pressure here and then add. I get 222,577 pascals, so it would be about double what the pressure would be on the surface.